Now I want to present you one of the most interesting examples that you could use it in your simulations. Assume that I give you any arbitrary CDF and I ask you to write a program, a MATLAB, a simulation program, which can generate data for these specific CDF or PDF given to you. How you would generate random variables which follow this distribution. So this is one of the ways we will solve one example, and then we will, in another example, we'll see how we could use the solution of this example for generation of random values. So in this example, the example is very simple. Let us know that the CDF of a continuous type random variable is given by a given function. So this function, the CDF, is given to you. And the function g of x, because the CDF is a deterministic function of x. So question is that, can I define a random variable using this g of x? Can I define u equal to g of x? Now, and what is the distribution of that? So I use this function, which is my CDF, and then I denote it by u, and I want to find the distribution of u. So the question is, what is the distribution of u because I have this random variable x, and then I have CDF of that, I put it fx of x here, and then I have u equal to fx of x. Now, this theorem says that provided that this distribution is a continuous type, is a continuous function, this has always a uniform distribution in the interval of 0, 1. Later on in the following example, following section, I'll show you how we could use this example to generate any arbitrary CDF. Now, let us prove this theorem. This is a very important theorem. Now, the first step is that I have u equal g of x. If I want to solve it, what will happen? Because g of x is a CDF function. The CDF function always ends up to be equal 1 and always starts as 1 and is a continuous function, so it's increasing. So for all values of u between 0 and 1, when you draw it, you have at least one solution. If u is outside of the interval, is above 1, or if it is below 0, if it is not in this interval, you don't have solutions. So for u not being in the interval 0, 1, the PDF of u is 0. So this is one part. Now, if u is between 0 and 1, okay, you have only one solution. So this equation, if I try to solve it, u equal to g of x always has a solution. So fx inverse of u is going to be your solution. Okay. So by definition, if u of u is probability that u is smaller than or equal u, and this is equal probability, u is what? U is fx of x. So because u is fx of x is smaller than or equal u, you could apply the inverse of these, okay? And because this is monotonic function, so you could say that this is equal to this guy. And obviously, this guy is fx of this random variable at this point. And application of the function on its own inverse is equal to u itself. So you see that this guy between interval of 0 to 1 should be a ramp, and here should be 1, and so on, because it cannot decrease and it cannot be bigger than 1. Here it cannot decrease further below 0 and should be 1. So therefore the proof is complete. Now, I want to see how can I use this theorem in order to generate in simulation a random variable x with a given continuous CDF. Okay, so what can I do is that I could generate a uniformly distributed, because I know that U is uniformly distributed in the interval of 0 and 1. And MATLAB, you can use rand of some numbers, and it will quickly generate for you uniformly distributed random variable between 0 and 1. So if I calculate from this expression, if I calculate x is equal to fx inverse of u, okay, then a distribution of these is going to be equal to fx of x by virtue of the theorem we have proven. So the question is that we could transform a uniformly distributed random variable between 0 and 1 to random variable x. So we transform it back to x and we get the CDF of x. So this can be also proven that if you have a random variable u and you generate x via this formula, if this is given, so what you need to do is to, if the CDF is given to you, you calculate the inverse formula for the CDF, you generate a uniform random variable, apply to it, and then you get the distribution you want. So this is just a simple suggestion to generate it this way, and then the rest of this example proves that the CDF of x is actually the CDF that you want. So you generate a uniformly distributed random variable, and then you apply the inverse of your CDF to it. In this chapter, we have learned how to characterize the statistical behavior of a function of a random variable. We have learned how to generate a given distribution. We have learned systematic methods to characterize the behavior of random variables which are interconnected.